BSc Physics Honours from Scottish Church College and MSc degree from the University of Calcutta. He was actually, he had the legendary Shotendranath Bose as one of his advisors during his MSc. And then he became the first student to receive the PhD degree from IIT Kharagpur in quantum physics in 1958. Receiving a Sloan Foundation Fellowship in 1959, he joined the University of California at Los Angeles for his postdoctoral studies. In 1961, he joined the Quantum Electronics Division at Xerox Electro-Optical Systems, Pasadena, and began his career as a laser scientist. Dr. Bhaumik is a physicist, best-selling author, celebrated lecturer, and most importantly, a philanthropist. He invented the world's first efficient excimer laser in 1973. This invention is epitomized by the development of the immensely popular LASIK eye surgery. He's also the author of famous books, Codename God and The Cosmic Detective. And he's the creator of award-winning animated TV series Cosmic Quantum Ray. He has been involved in numerous community activities. The most recognized of his philanthropic activities is formation of the Bhaumik Educational Foundation in Kolkata. With his generosity, the UCLA established the Lal Bhaumik Institute for Theoretical Physics in 2016. Dr. Bhaumik has won many awards and honors for his achievements, amongst them Padma Shri, Pravashi Bharatiya Samman, Mahatma Gandhi Humanitarian Award, Award for Outstanding Achievement in Science and Philanthropic Contribution, Chaudhary Award, as well as Fellow of the American Physical Society, IEEE, the Asiatic Society, and the Honorary DSc from IIT Kharagpur. He has been listed in Who's Who in America and in American Men and Women in Science in 2006. It is really our pleasure and honor to have him. Dr. Paul.
Okay, I would like to request you all to put your mobile phones in silent mode before the lecture begins.
Director Samamitra Banerjee. It is a distinct honor to be in a place which is famed and well known since I was studying in Calcutta and Kolkata now, of course, I should say, but never had an opportunity to come here. And I know that you have maintained what a good institute should be. You heard the Nobel laureate talk about the three ingredients: excellence, excellence, excellence. You excel in what you do here, especially in the area of statistics. Now I believe you're doing quantum computing, cryptography, and also other natural sciences, as well as I believe there are some physics and mathematics activities here. So I don't know, I believe that the audience is here diverse of background. So, not knowing what I should be talking about, I thought I took a guess of talking to you about my present subject of research, which is there objective reality in the wave function, which is the basic tool that we use in quantum physics. Why? Well, quantum physics is not out there somewhere. It really is at the foundation of everything that we deal with, chemistry, biology, and even statistics, which is now going to be in quantum computing. And yet, even though the universe is quantum at the core, ever since quantum physics began, about 90 years ago, it really has been an enigma to most physicists, especially Einstein was not too happy about the fact that everybody was so enamored and buoyed by the success of quantum physics calculation, which agrees with experiments for the first time so precisely, as you probably know, that one of the most precise calculation is about the spin magnetic gyromagnetic ratio of electron, which has been calculated up to a 1 part in trillionth and experimentally verified to that extent, which is one of the really amazingly precise verification of a theory. And so most of the physicists were not bothered about what is this wave function, why we need that, why is it always associated with what we think is a classical particle. Einstein tried to really, along with Schrödinger, who is the father of quantum wave mechanics, and the person who actually got this initiated, De Broglie, with his proposition that, which is actually, it was a PhD thesis, in which he proposed that by that time, with Einstein's proposition that radiation, which everybody knew by that time was an electromagnetic wave, but Einstein said the radiation actually comes in particles called quanta, quantum particles called photon. So he was the first proponent actually of wave-particle duality. That radiation by the time was so established by Maxwell's theory, by demonstration of Hertz, and that electromagnetic wave actually goes through space freely, and also that the diffraction experiment by Young, it is almost ingrained in people's mind that radiation is nothing but electromagnetic wave. Einstein was the first one to propose that it actually consists of discrete quanta that we now call photon, and he offered the photoelectric effect as a proof of that. But he stunned everybody. Everybody was so ingrained in their mind that radiation is nothing but a wave. How could it be a particle also? So much so that even 10 years after, Max Planck, who is considered the godfather of quantum, because he used for the first time that a black body radiation actually has to come in quanta in order to explain what we call the ultraviolet catastrophe, meaning that equipoise of energy means that all particles share equally. But then what happens is that when you go to higher energies, then the same number with the higher energy shows that you should get much more higher intensity. But in experiment, actually, we see that it falls off in the ultraviolet. So out of desperation of 8 years of frustration, actually, he came up with a mathematical model that energy must be absorbed and emitted by a black body in quanta. And that was the famous E equals h nu that he submitted. But he himself did not believe in it. He told his friends, it is just a mathematical construct. I needed to find a black body curve, radiation curve. And as I said, even after 10 years after he proposed that, when he was introducing Einstein along with Nernst and others to be member of the Russian Academy of Sciences, he chided in a way to Einstein that he's a great scientist, but sometimes he come up with some odd ideas like radiation consists of photon, which he himself said was necessary for finding the emission curve of the black bodies. And Einstein, of course, said that not only the black body emits and radiates, but radiation itself is consisting of this quanta. And as I said, he was the only one who stuck to that. Everybody thought that he was out of his mind. How could radiation be consisting of particle? Nernst was in the committee. He said, that's the craziest idea I've ever heard. And even Niels Bohr, when he did his first atomic model, Bohr-Rutherford model, that electrons have stabilized discrete orbit. And he didn't believe in photon either. So it would be natural for him to show that when electron goes from one orbit to the other, the radiation come in quanta. Instead, he thought that it will continuously radiate until it reaches the lower level. So until Compton showed the Compton effect, where that X-ray photons were actually behaving like a billiard ball when it was colliding with electron. Up until that time, nobody gave any credence to Einstein's idea of photon, and in that matter, the duality of wave and particle. And after that, the young Louis de Broglie, in his thesis, he proposed that if light can be radiation wave as well as a particle, why not matter? Matter should have a wave property also. When he presented his thesis to Lajma, his director, he said, that's the craziest idea I ever heard. What could matter have in your wave? So, but he was Prince, so Lajma sent it to Einstein that it seems a little bit crazy to me, but what do you think of it? Einstein immediately gave the highest recommendation. He said, de Broglie has lifted the veil, lifted the corner of a big veil. And he gave his support, and he said later on that he himself actually came up to the same conclusion but didn't publish it because there was no evidence. So not only de Broglie got his PhD, but also when in his oral examination was asked, how do you know matter has a weight? He said, we have to look for it. And Einstein supported that wholeheartedly, asked everybody, look for matter wave. And accidentally, there was a incident at RCA, Bell Lab, not RCA actually, Bell Lab, by Clinton Davis and Lester Gartmeyer were studying vacuum tubes for communication purposes actually. And one time they broke and the metal got oxidized. And so they thought in order to get rid of the oxygen, they heated it. Unbeknown to them, it became crystals, nickel crystals. And when they shined the electron beam on that, lo and behold, they indeed found that the electrons have wave property also, because they're seeing diffraction pattern, which only comes from wave. Well, that was the proof positive, and started the quantum mechanics in full gusto. And Schrödinger actually, in Zurich, where Einstein used to be, a teacher for a while, and student too. He was giving a seminar at the Zurich Polytechnic, ETH they call them, about the exciting news about that de Broglie's wave hypothesis. So I think it was Dubai who said, "So what have you done?" So he took it as a challenge, went to the mountain, and came up with his Schrödinger equation, that is a basic tool that we use for non-relativistic quantum physics. And just a few months before that, Heisenberg actually also formulated quantum physics in a abstract matrix mechanics using that. And of course, Schrödinger showed that both the formulation, even though look so different, they actually are equivalent. So anyway, that's how quantum physics came to be, and immediately it was applied to the hydrogen spectrum. And it's actually such a tremendous agreement with the experimental result that people have no doubt that that was the correct way to go. And success after success, buoyed by more success, people went to that direction. Well, Einstein, who actually is in some ways considered to be the father of quantum physics, he said, yes, that's fine, but what is this wave function? Is there any objective reality to that? And Niels Bohr, of course, led the charge, saying that who cares? It works, shut up and calculate. And it's not our duty as a scientist to say how nature works. Our duty is to predict results that can be verified. And most people kind of follow that dictum. Only a handful of people, de Broglie himself, Einstein, Schrödinger also, and later on David Bohm, they always thought that wave functions should have a reality. In classical mechanics, we use sort of a tiny marble type of model for the object, but that just doesn't work in the atomic dimension when you go to like micron or at least to the atomic dimension of angstroms. So for a long time it remained kind of dormant, whether wave function does have reality or not. Recently it has been revived by the people like in your discipline, the quantum information theory people, because it seems like it's necessary to know whether wave function has an objective reality or not. Hardy has a theory, and Renner and Colbert, who is Renner is at Zurich also, they have a theory, but the one that is getting traction is by U.C. Barrett and Rudolph. Rudolph happens to be the grandson of Schrödinger. Their proposition, of course, is the calculations are based on quantum information theory. What I have been trying to do recently is to use actual physical properties like energy, momentum, for a single particle, because as soon as you go to more than one particle, it becomes, you have to go into coordinate space and eventually to Hilbert space, where the thick smoke of the heavy artillery of the Hilbert's mathematics sort of shrouds the reality. But my proposition is that if you can show that a single particle has the wave function representing a single particle has reality, then obviously ensemble of them ought to have a reality also. So I'm approaching from this point of view some physical properties, and I believe I have a plausible model that I have presented, and I just published another paper in December. Before that was last year, which is called "Was Einstein Wrong on Quantum Physics?" It's a bit of a technical paper, and I might go over that a little briefly. But what I like to tell you what it's all about. How did I come to this thing? How do I come to this idea? Actually, I was looking for unification of fields, that all the fields that are explicitly manifest in our day-to-day world, along with the other matter particles, it seems like they all come from one single field. That's why when I was talking to the Nobel laureate, that I'm almost obsessed about unification, which Einstein first introduced in science. Before that, nobody ever thought about it, because everything is so different in our day-to-day world. It is hard to imagine that they could come from really one single source. But the clue came from some observation that is incontrovertible. Let's take, for example, an electron. No matter where an electron is produced or when it is produced, at the Big Bang or through the astrophysical processes happening over the eons, or in the laboratory anywhere in the world today, electrons are all identical, exactly identical. Their mass, their charge, their spin, their magnetic moment, quantum number, all of them are exactly similar. And on top of that, electron has an antiparticle called positron, which have same energy or mass, but opposite charge and opposite spin and other properties. But what happens when you bring the positron to electron? It immediately get destroyed into energy. So that means that electron, even though we call it fundamental because we cannot divide it anymore, but it is not really really fundamental, because it's so easily destroyed under the right conditions. So those two give us some clues. What could it be? One obvious thing that comes to everybody's mind is that if they're exactly the same throughout the universe, as big as the universe is, and always the same since almost the beginning of time, beginning of the universe, there must be something underlying that actually gives rise to the electron. Wouldn't that make sense? But we didn't have any model of what could it be that could give us. And it so happens that when you combine special relativity with quantum physics, and then you come up with what we call quantum field theory. It is pretty involved. It involves pretty esoteric mathematics, but it has been extremely successful in describing our reality. I'll just quote 3 Nobel laureates about that, and everybody, of course, that I know of would agree with that. Steven Weinberg, Nobel laureate, who is still alive, he's probably the oldest, one of the oldest physics Nobel laureate alive. According to him, when you combine relativity with quantum physics, it's an inevitable outcome. The quantum field theory is an inevitable outcome. And David Gross, that you saw the interview, actually in the interview said that the unification is something that he was talking about the forces, similar to true for particle, is actually happened. So we have so far successfully unified the electroweak field, which consists of the weak nuclear field and the electromagnetic field. But they're so diverse. The electromagnetic field goes from one end of the universe to the another. There is no limit. We're seeing photons today from the very beginning of when they decoupled from the primordial plasma 300,000 years after the Big Bang. So those photons, the microwave background photons, they've been alive for this long, almost like 14 billion years they've been alive, and we are seeing them today. Yet the weak nuclear force, cannot get out of the nucleus. Its range is only 10 to the minus 16 centimeters. So they're so diverse that nobody could think that they could be really coming from one source. And yet, when you went to like what the universe was like, trillionth of a second after the Big Bang, it's actually with the quantum field theory. There are various quantum field theories, but the one that we are talking about is what we call quantum field theory of standard model of particle physics. Just like we have periodic table of elements, we have a standard model for all the observed particle, and one that we haven't seen yet, the graviton, but gravity waves detection indicates that the graviton should be there. What I was getting at is that these two diverse forces actually is coming from one single source, electroweak source. And then, of course, we have combined the strong force also, which we call with a grand unification, which combines strong nuclear force, weak nuclear force, and electromagnetic force. But you don't have a direct evidence of it yet, because it requires much higher energy than we can create in the laboratory. Nature, of course, during the beginning of the universe, had that kind of energy, so it must have been unified at that time. The two indirect evidence that we're looking for, one is what you call the neutrino oscillation. Standard model doesn't predict neutrino oscillations, so it is a physics beyond standard model. And we're looking for proton decay, and so far we have not been able to successful in doing that, but when that is done, that would be a pretty convincing proof that all the three what we call gauge forces actually come from one single source. Gravity has been the biggest problem to combine with them, and the most cutting edge research in physics at UCLA as well as elsewhere, is how to combine gravity with the rest of the forces. And of course, so happens that at the temperature that you combine the electroweak force, the what do you call the leptons, electron, neutrino, three different species of that, they become united, and the baryons, the quarks, and this more massive particle like that, they also become united. But the leptons and baryons are not yet united there. The theory shows that when we unite gravity, the quantum gravity will unite all of these particles as well as forces to one single unified field. So in our view today, particles are really, although we think about them as a tiny little marble, they have the same footing as the abstract fields. Talk about gravity, for example, or classical gravity that we live with every day. When you leave home, you don't think about it. We go about our life without even thinking about it. Here it is, present everywhere, but it is abstract. You cannot see, you cannot touch, but it is substantially real. But this gravity, of course, is a classical gravity. By that I mean that it has a source and it falls off in strength as you go away from the source. When you go to space, for example, the gravity becomes weaker, and we have seen pictures of astronauts tumbling around without any gravity. And in fact, as you all know, that if you go to moon, because moon's mass is lower, your weight will be 1/6. Good way to reduce your weight. Go to moon. But the point I'm making is that is classical gravity, but it originates from quantum gravity. And quantum gravity does not have a source. It is its own source. And it is the same, exactly the same, everywhere throughout the entire universe, where you are, where you are not. And so is all the other forces, the three forces that I talked to you before, as well as the particles. In quantum field theory, we put particles in the same footing as the forces. They all come from an abstract entity, what we call quantum fields. Now the question is, as of now, that's the ultimate objective reality, the quantum fields, which in our day-to-day ambient, they're all separate because we need that for manifestation. But if you go down towards Planck's dimension, the ultimate smaller unit of space, it will gradually unite, and near Planck's dimension, it will be just different aspects of the same entity, same field. So, as I was talking to the Nobel laureate, and he said, that's fully agreed with that, is that even though we are not able to go there, but we have a pretty good quantitative evidence in the way that if we extrapolate these measured strengths of all the forces in an ambient condition and extrapolate them to higher temperature or equivalent to smaller distances, lo and behold, they really become one, or different aspect of the same one. That's why I wanted to show you that video. This is something, is a pretty good indication, even though we do not have fully demonstrated unification yet. And the the thought is that the quantum field theory of Standard Model is really, at this moment, our latest objective model of objective reality. As you know, science is an open-ended field. The more we know, the more we realize how much we don't know. But what we establish once, it never goes away. Like Newton's law still holds. Sometimes people wrongly say that Newton's law has been overthrown by relativity. And that's not correct. Newton's law still holds under its own in its own domain. We still use Newton's law to devise spaceship, rockets, and all the gadgets we do. But when I go to a different circumstance, namely higher velocity or stronger gravity, then Newton's law has to be expanded, not thrown out, expanded by relativity. For the speed, we use special relativity. For the gravity, we use general relativity. But the point I'm making is that once something is established in science, by the gold standard being experimental observation, it has to be experimentally verified. Just to give you an example, string theory is a beautiful theory, but it has no prediction that can be experimentally verified so far. So it is not accepted as a established science. But we know that we didn't have to take any Nobel Prize in physics back. So what is established, that in its area will always hold. So the energies that we deal with, quantum field theory is well established, and of course it is not the last word. At the moment, that is what we know to be the objective reality. We still don't know what dark matter is, what dark energy is. We do not know how the physical constants are so exactly the value that they have. So obviously physics is going to march forward, something better, newer will come. But the reality described by quantum field theory will still be valid. And this is why one of David Gross's student, Professor Wilczek, who also, he was actually his first student who also got Nobel Prize. He says that quantum field theory is very good in describing the reality we happen to inhabit. So I think that is pretty well established that we can base some theory on that. And this is what, the unification is what got me motivated, and from that I realized that why not use quantum field theory to describe the objective reality of the wave function. And I have written quite a few articles. The last two ones I gave copies to your esteemed director. So it's also in a refereed internet journal called Quanta Journal that you can look up also in the archive. I'm trying to publish that in Science now. But so far I think people gave it a good reception. But the presentation is a little bit technical. I don't know how much time do I have. It's already 5 o'clock. And there is some question and answer. Can I just briefly describe to you? I think that if I go into my PowerPoint presentation, it probably takes a lot more time. So, as I mentioned, that the quantum field theory says that everything, matter, particle, or force particle, their excitation of the underlying quantum field. which is very abstract, just like gravity, and in fact more abstract than gravity, because gravity falls off and the quantum field does not fall off from one of the universe to the other. And so it's excitation, quanta of excitation. But any one of you who know math, and the waves, properties of waves, that a quantum of excitation with a definite energy and momentum will have a single frequency, a sine wave. And that goes from, you cannot localize that. But a particle, we have been taking as a wave packet, because it has to be a Fourier combination with proper weightage of the various frequencies to build a wave packet from a wave. So how does a pure sine wave that comes out of the quantum field becomes a wave packet? I have utilized the fact that even though electron by its, even a single electron is its own reference frame, is not alone, it's always being bombarded or interact by the, what we call the quantum fluctuations, which essentially means that the electron field is interacting with all the other fields. In fact, it is pretty much assumed that any particle like electron, as soon as it starts into existence, it becomes subject to this interaction with all the other fields. So they're always interconnected in a way. So the sine wave becomes distorted. And we know from Fourier analysis that no matter how distorted a wave packet or wave form is, you can always build a Fourier integral to describe it. And so there is our wave packet. And that's what, you know, my basic proposition is. But then we have another complication. Before the Higgs field became manifest, about a trillionth of a second after the Big Bang, when electroweak unification ended, electromagnetic field and the weak field became separate. It also, the Higgs field becomes manifest. Before that, all the particles, electrons and all the quarks and all that, along with photons, they were buzzing around the velocity of light. But as soon as Higgs field came in, it started interacting with these particles to a different extent. Photons and other bosons, integral, not all the bosons, the weak bosons have mass, but gluons, gravitons, photons, they do not interact with the Higgs field. So they move with the speed of light. But matter particle, the electron, they acquire mass. In fact, what is mass actually? Using Einstein's word, his first paper where it was famous equation of E equal mc square, it was not about E equal mc square. In fact, the title of the article was, does a particle energy acquire inertia, has inertia. So Higgs field gives the inertia to slow the electrons down. Of course, at the very beginning, the energy was still high, so they were pretty close to the velocity of light, but they were at the time, electron and positron were being copiously produced and annihilated until the temperature cooled down below the threshold of the sphere production. Then that's about a pretty late stage in terms of the initial condition of the universe. But when the Piat production threshold was reached and the electrons and positrons united, but because of some asymmetry in what we call the baryogenesis, only one part in 10 billion electrons survived. The rest of them all became photons, and that's what we see as the microwave background radiation today. And most of or all of the electrons that we deal with today, they all have their origin during that epoch of the universe. And today we, in order to get the electrons, either use a heated filament or use a photoelectric effect, assign a photon of large enough of energy to erase the electrons. That's a more elegant way of getting the electrons actually to study. But what happens is that eventually electrons come to a very small velocity, almost then at rest, close to rest, within the uncertainty principle. But the energy is at rest. The particle is at rest, but the energy is not. Energy inside the electron, even at rest, is vibrating with a very high frequency, like 10 to 21 cycles per second. So what happens when the electron starts to move? Special relativistic effect kicks in, and then the wave packets become phase modulated. So the de Broglie wave is not really a separate wave on its own. It is a phase modulation wave. And of course, phase is most important in determining the trajectory of the kinematics of the particle. But of course, when you determine the amplitude of any quantity, then you have to multiply, because these are complex quantities, you have to multiply the complex conjugate, and so the phase factor goes away, becomes 1. So you mostly deal with the square of the amplitude for predicting probability. So that is something that Du Bois actually thought about, but all his life he struggled with that. So he thought that the wave was actually a fictitious guiding wave. Particle was still a particle, classical particle, which of course people didn't take it to be true. And David Bohm years later tried to revive that, saying that what he called fictitious wave actually is what he showed is a quantum potential, what he called a quantum wave rather than a fictitious wave that guides the particle. Not too many people really adheres to that view, even though it predicted this non-locality that Einstein proposed in 1935, called the EPR effect, where now it's being used in quantum computing. So that's why the interest in the reality of wave function has been revived. And what I have been doing is complementing the systems part of it, where you have more than one particle. And the work by Q.C. Barrett and Rudolph shows that quantum, from the system's point of view, the wave function actually have objective reality. And what I have been doing is supplementing that when you look at it, at least for a single particle from physical measurements, I'm using physical quantities like energy momentum. The wave function is not a mathematical construct. It is based on reality. Mind you, it's not classical reality, it's quantum reality. Right? So what's the difference between the two realities? In quantum reality, if you take one single incident, let's say a radioactive atom, we have no way of predicting exactly when it will decay. It could decay in the next millisecond, it could decay a billion years from now. You have no way of predicting. In fact, I know that you have a cryptography group here, and you generate the keys using computers, but this unpredictability of single event in quantum physics is even surpasses any computers that we have, any digital computer that can predict. So quantum cryptography has been one of the first use of this non-locality that Einstein proposed to show that quantum physics is not complete. Well, in that respect, it turns out that quantum physics is complete, but it doesn't follow classical reality, it follows quantum reality. And again, getting back to that, even though you cannot really predict one single event when it would happen, but if you have ensemble, then the average can be eminently calculated and predicted. For example, we all know that you can calculate the half-life of the radioactive decay and so the quantum mechanical average of many atoms or many particles, many systems, they are predictable, so there must be some self-referral. Because if each individual is totally predictable, how could the ensemble be predictable? There must be some self-referral. And again, another of my interest is that possibly that is the source of our awareness, because our consciousness is based on our awareness. There is self-referral system. That's something that I've been working on also. So what I'm getting at is that the work that I presented on the reality of the wave function is related with the unification, but unification that we've been talking about is of everything physical. It doesn't include our consciousness here. And we know that our consciousness also is a reality, because it is, after all, the window through which we perceive everything, science, our emotions and sorrows and joys that colors our life. So it's the very window through which you perceive reality. Consciousness is an instrument of perception as well as it is a perceived entity. What do we have in the universe that is similar to that? Nothing. So it must be a fundamental aspect. If it is a fundamental aspect, we have to also unify with the unified field that we talk about with the matter, physical objects and forces. Well, as of now, at least we have to consider, just like at the beginning of quantum physics, Bohr said that the principle of complementarity. When you cannot explain something, we have to say that it's two aspects of the same entity, and so that's where we stand. But I think, as Roger Penrose has very rightly said in his seminal book, The Emperor's New Mind, that if science cannot combine consciousness with our scientific discipline, then we cannot really claim the legitimacy of completion of our scientific worldview. And he believes that someday we will be able to combine not only all the forces of nature and particles of nature, but also will combine consciousness with that. And that's why what I found interesting is that the talented rishis of our Vedic time, they came up with that conclusion of Brahma, that Brahma is the source of everything as well as of consciousness, and it exists being intertwined with everything in this universe, you, me, table, chair, everything. as you probably know, the saying, Sarvam Khalidam Brahma. Brahma, the source, the one source, exists in an intertwined way with everything. And for us, for example, we are all made of particles. And those particles are coming from, again, not only a unified field, but they're always interacting with each other. So we are always entwined, inseparably intertwined with the source. And when we come to realization of where consciousness arises, and then of course, that will complete what our this is cognized purely through contemplation. Of course, when you come to some knowledge through mere contemplation, it could be right, it could be wrong. In fact, today they say, what happened to those theorists or the philosophers of yesteryear? But they have all become theoretical physicists, and they can predict. They can come up with answers to many things. Like, for example, recently there was a bomb at the LHC in Geneva at 700 GeV, and it was not up to the gold standard, which is the statistically has to be 5 sigma correction. It was only 3 sigma, but as soon as it was released, with that caveat, this is only 3 sigma. 30 papers appeared next day by theorists, they are so productive. And it turned out to be a fluke. The experimental result was a fluke. So all those theoretical work went into the garbage can. So theorists are very fertile in that sense, but we have to verify with the gold standard of experiment. And this is why I don't know. Can I continue about 5 more minutes? Ever since humans started to think, all thoughtful person, one time or another in their life, ask the questions, why I'm here? What, or if anything, brought us here? What for? Well, at the very beginning it was answered by religions, but today in our scientific world, scientific thought, bent of mind, it doesn't satisfy us, because in religion, first tenet is thou shalt not question. In science, it's just the opposite. Thou shalt question. Don't take anybody's word for it. You've got to find it yourself. So it's not compatible in that thinking. Then, of course, after religion came philosophy. Again, as I said, philosophers can give you good arguments why something should be true. They can give you equally good arguments why it should not be true. So the gold standard is experimental observation, and that's what science is based on. And so is our society in our real. People are saying, what is reality actually? Well, we have some reality in our dreams. I cannot communicate my dreams to you. You cannot communicate your dreams, reality that you see in a dream. But our society as well as science depend upon a accepted definition of reality. That what I see and you see, and we communicate that we are seeing the same thing. That's the basis of reality we have. And on that basis, we have come up with science that has produced technology that's given us abundance that our forefathers could only dream of. So we have an innate tendency to believe in scientific method. That's why what our rishis cognized, since it is now anchored in science, we have to take that as a reality, in the reality that we define. So if we can actually get that on our belt, every man, woman and child in this world would understand that we are all coming from one source, we are always inseparably connected to that and to each other. Would that be a wonderful world? I think it is necessary to improve the quality of our mental life. So science could actually contribute more to our happiness, which is what we need, what we want at the end of the day, more than what it has done in the material world.